Hello students, my name is Shashank Shekhar. So we started the chapter Electrochemistry. So let us continue our discussion. So today is the second lecture of this chapter called Electrochemistry. So yesterday basically we have seen the types of cell and we are mainly focusing on what is redox reaction. Today we will see each cell in a more appropriate manner. So if I talk about the syllabus, so today we will be studying this EMF of a cell. So to study this EMF, we have to know certain things. We will, and those topics are, so first one, we will know more about this galvanic cell. In the previous class, I have given you an introduction of this galvanic cell, but in today's class, I will show you how it works. What are the reactions that goes inside a galvanic cell. So then we will see what is electrode potential and how does the galvanic cell works, means the chemical reaction that goes inside it. Then I will move to this functioning of salt bridge. So there is a component called salt bridge. So we will see what is the use of that salt bridge and how does it help to complete our circuit. Then today's topic, which is the main focus. So we'll see what it is EMF, what is EMF and how can we calculate it. Then we will see a way in which we can derive, or you can say, so not derive, we can say we can symbolize whole of the cell with the help of one equation. So we'll see how we will represent that whole cell with the help of an equation. Right. So let us start our today's class. So first thing, the galvanic cell. So I have mentioned about this in the earlier class also. So what is galvanic cell? It is something that converts our chemical energy into electrical energy. And whose chemical energy? In spontaneous redox reaction energy. And this chemical energy is Gibbs free energy specifically. So what type of chemical energy? Gibbs free energy. Now you will ask what is a spontaneous. So I mentioned in the previous class also. I am saying it again. Whose delta G is negative. So if a reaction is having a delta G value less than 0 or a negative value, then it will occur spontaneously and the energy that is you can say produced is used to make our electrical energy. So the chemical energy, the Gibbs free energy is used and electrical energy is produced. So if we talk about an example, so this Daniel cell I have discussed earlier also. So it is a type of cell, or you can say an example of galvanic cell in which we use zinc and copper. And it is having a redox reaction occurring represented by this equation. So we have zinc and we have Zn2 plus, we have Cu2 plus going to Cu. Now let us make a small illustration here so that you can remember previous class. So for those who do not remember, so you should be aware of the species that is going reduction and species that is going oxidation. So if I split this reaction into two halves, so I have told you earlier also that electrochemical reactions are those in which we can separate the oxidation and reduction reaction in different compartments. So suppose the reduction half cell is this one. So this is the reduction half cell. How? We have taken copper. Now copper is present in 2 plus on the left hand side, and as we move from left to right, we can see that it is moving from copper 2 plus or salt to the metal. And meanwhile in this process, it is gaining 2 electrons to neutralize the positive 2 charge, and we are getting CuS, right? CuS means solid. Again, here AQ means aqueous. This Cu2 plus is present in water form. I mean here that we know that copper cannot, Cu2 plus cannot be present as a independent species. So it must be a salt, CuSO4 or CuCl3 or anything. And now this salt cannot be present in concentrated or 1m concentration. Why? Because we have to make a solution, and this copper sulfate and all of these are in crystal form. So what do? We dissolve it in water to make a solution, right? So this Cu2 plus or this salt is present in aqueous form. Here aqueous represents that we have dissolved this copper into water. Now this S solid represents that we have pure copper. Okay, so pure copper metal. And this is the reduction half. Similarly, we have the oxidation half, in which we have Zn solid, means zinc metal we have taken, and this zinc metal is going into the solution, which is aqueous in nature, and again we are getting a salt of zinc, which is dissolved in water. And here you can see that this Zn is giving 2 electron. So it is kind of oxidation half reaction. So you must understand this, what is a reduction half reaction and oxidation half reaction. Now if you add both these reactions, so what will happen? We will get on left hand side Zn plus Cu2 plus, and this 2 electron will be cancelled out. Similarly on the right hand side we will get Zn2 plus Cus. So this is an Daniell cell. Okay, this is an example of galvanic cell which is called as Daniell cell, in which we use copper and zinc. So this was all about the a theory part of the galvanic cell. Now we'll move to its functioning, more appropriately the electrode potential. So what is electrode potential? So you need to understand this very clearly. So from the previous class we know that we have an arrangement of 2 compartments, right? And in one compartment we have an electrode, and in another compartment we also have electrode, and both these electrodes are connected by a wire. So what I am doing here, I am taking a compartment outside to think what is happening in that compartment. So you have to imagine it like this. So we have taken a compartment, we have put the electrode, no connecting wire, nothing is connected to it. Now what we have in the solution, so let me make it clear for you that what is in the solution. What do we take in the solution? So we take 2 things in the beaker and in the metal. So the metal we take is, it can be any metal, it can be zinc, it can be copper, iron, any metal. And the solution that we are taking, in which the metal iron is dipped, in which the metal rod is dipped, is the salt of that metal. Okay, what is it? It is the salt of that metal. Now there are exceptions to it, in cases we have a hydrogen type of electrode which is gaseous in nature, so we cannot take the solid form it. But if the solid form is present, right, if the solid form for this metal cation is present, or the metal is present, we will take that metal and dip it into electrolyte which is containing the salt of that metal. Now what will happen? So there is an interface. What kind of interface? Between the solution and the electrode. There must be a boundary, that is why that they are separate. Now on that interface, the metal has a tendency, to go from your metal form, say from your metal form to your salt form. How? By donating 2 electrons. So initially the metal must be present as a neutral atom. Now if it wants to go into the of course your solution, it has to lose 2 electrons to go into the solution, or 1 electron depending upon the oxidation number, right? But it cannot do so. Why? Because that process will introduce electron, and there is no way to escape the metal. So I want to make a point clear. So there is no potential difference, there is only potential. Okay, so current will only occur if there is a potential difference. So there is a potential that your metal can donate cation to the solution. Yes, this is true. Now the next point, this is the first point, that there is a tendency of metal ion from the I will make this point on the later phrase, but I have explained this one. The metal atoms of the electrons have a tendency to go into the solution as ions and leave behind the electron at the electron, trying to make it negatively charged. Yes, if this will leave the electron on the electrode, it will make it negatively charged. So this point I have explained. Now at the same time, there is salt present in the solution, right? It is true. Now it has also the tendency to gain 2 electrons. Since it is positively charged, it has a tendency to gain 2 electrons and go into your solid phase or deposit on the electrode. How it will do? It will take 2 electrons from the solution and deposit on the metal electron. So there is also a tendency or a potential to do so, but there is no potential difference. So this process will not occur until and unless we connect it with a wire. So that thing will take earlier. So we just have isolated one compartment with one electrode dipped in the solution. And the second tendency I have mentioned is that the metal ion from the solution will try to deposit on the metal electron, trying to make it positively charged. Okay, so it will try to make it positively charged. How it will make it positively charged? So as this Cu2 plus will move, okay, so how it will move? As it will deposit on this, say, electrode, since this is positively charged, so the metal will become positively charged, but it will not occur also. Why? Because there is not a potential difference. Now, there is a potential difference that develops between the electrode and the electrolyte, which is called electrode potential. Now, there were two independent potential I told you earlier. Now, as a complete, there is a potential difference now, in which one has the tendency to go inside and one has the tendency to go on the metal. So there is a potential difference, but since there is no complete circuit present now, the second condition is also that there must be a complete circuit so that this accumulation of charge after the deposit can be neutralized. But since there is no such way or such method to do so, so it will not happen. Okay, but there now is a potential, electrode potential difference. So we have discussed one compartment. This case is on both the compartments. It can be applied on both the compartment. Now what will happen? When we will connect two such compartments through wire. Okay, what we will do? We will connect two such compartment with wire, and depending on the tendency of both the compartment, oxidation or reduction will take place. Okay, so this is a very critical thing. So most of the times we avoid this criticalities, but now I am just explaining each of these steps, what is happening right now. So the overview I will give you at last. So what is the overall process? But now I am just defining each and every process minutely. So the thing I have told you earlier, there are two possibilities. Now we have connected both these compartments through wire. This is our wire. Now there comes the comparison. If this electrode, say this electrode, it has more tendency to accept electron, or you can say that it has more tendency to become positively charged. How? By taking Cu2 plus. How? By taking Cu2 plus, or say you can say oxidation. Now what will happen? The two tendency will try to compete each other, and depending upon the tendency, suppose it has a greater tendency to lose electron, okay, and it has a greater tendency to gain electron, then in that case what will happen? The electron that is lost by this, I have told you earlier that Cu will go into the solution and the tendency to go into the solution. Okay, so this metal has a tendency to go into the solution. At the same time, this liquid has a tendency to go on the metal electrode. But suppose the going of this metal into the water, its tendency is more. So in that case, what will happen? This metal will go into the solution and will generate 2 electron. Okay, this will generate 2 electron. At the same time, we have this compartment which is losing 2 electron. How? Because this Cu is going into the Cu2 plus. So it is losing 2 electron. Now this electron will travel through the circuit and will come here. And this Cu2 plus, which is present here, will take up this electron. So in a nutshell, I want to say that. So I have told you all the equilibrium that exists there. Now I will tell you in the nutshell what has happened. So on the left side, I have told you that the oxidation takes place. So what is oxidation? The loss of electron. So this zinc will lose electron. It will go here through the circuit and move on this metal. Now negative charge is developed on this. Now copper ion is present here, but it's positively charged. This copper ion will take electron from here and settle on this electrode. Now this will get thicker and thicker. With respect to time, what will happen? So since this zinc is going into the solution by depletion, by releasing electron, So this will get thinner and thinner with respect to time, and this will get accumulated with more and more zinc. Okay, so this will get thicker and thicker. Now due to this reason, there is a flow of charge. You can see here that electron is going from here to here. So why is it so? Because there exists a potential difference between the two electrodes. There is a potential difference between the two electrodes, and also there is a circuit. Now if you consider the direction of current, so since the electron is flowing through this direction, the current by convention is taken in the opposite direction. So you must have seen these things in physics also. So it says that whichever is the direction of electron, we take the direction of current opposite to that. So this is how a galvanic cell works. Now let us move to our next thing, which is salt bridge. So what is salt bridge first of all? So we have seen a salt bridge here. What we have seen, this salt bridge. It is present here. So what is this salt bridge containing? This salt bridge is containing agar-agar solution. Agar-agar solution, which is made up of either sodium chloride or potassium sulfate or sodium nitrate. So why is it so? I will tell you in the next slide. Now what does it do? It permits the passage of electric current internally. It's very important that if you see the two compartments, it's look like this. Yes. Now it is not a complete circuit. You can see very clearly. So to complete the circuit, we put a salt bridge. Now if you follow my red dot, you can see a complete circuit like this. Okay, so this is a complete circuit, a closed circuit. What does it do? It maintains the current internally. Second, it maintains the electrical neutrality. So I will make you understand how is it maintaining the electrical neutrality in the next slide. Again, if we do not keep it in two compartments, if we do not have the salt bridge, we have to keep it in one compartment, and that would mix both our, say, copper sulfate and zinc sulfate, and that will result in a reaction or something like that. So it also in a way preventing the intermixing of solution, and it does not take part in cell reaction. This is the most important one, that this salt bridge never takes part in cell reaction. So 4 of the points are: first, electrical neutrality, first, complete the circuit; second, electrical neutrality; third, preventing intermixing of solution; and fourth, it does not take part in reaction, cell reaction. Now we'll see how does it maintain the electrical neutrality. So this is our, say, our diagram, which will help us to get a knowledge of how it is functioning. So initially, we know that on the left hand side, there is oxidation. There is oxidation taking place. So this Mg is losing electrons, and it is going into the solution and making Mg2+. Now this solution has a greater number of Mg2+, or it is not electrically neutral, because initially it was containing the same number of Mg2+ and same number of the other anion respectively, if it can be SO4 or anything. So it was electrically neutral. Now since the charge Mg2+ is going to the solution, so it will be not electrically neutral. Similarly, due to reduction, there is accumulation of anion on the right hand side. How? So suppose it is containing Ag, SO4. So if Ag+ is going onto the electrode and accumulating by taking an electron from this circuit, we are left with this SO4- or say 2-. So we will have an accumulation of SO4 2-. Suppose we are taking NO3- salt. So we are taking basically AgNO3-. So since Ag+ has gone onto the electrode, we are left with NO3-. So what do we see? We see that the Mg2+ have accumulated in the left hand side or in the oxidation compartment, and in the right hand side we have this NO3- accumulation due to oxidation or reduction of the silver. So what does it result in? So we have a charge here. So we have a charge, positive charge here and negative accumulation here. So what does it result? So if we do not put this salt bridge, so we'll see a small deflection in that circuit for a while. suppose this salt bridge is not present. Okay, so we do not have any salt bridge. Charge has accumulated, and now what will happen? We will see a small deflection in the voltmeter, and the current will stop. So in actual, what we are doing is we are removing this salt bridge and we are just connecting with the help of a wire. So it will result in a very quick, you can say a very quick deflection, and it will happen for an instance and the current will stop. You cannot just see it very quickly for a long enough time. For a small time it will happen and the current will stop and our reaction will be over due to accumulation of charges on both sides. Now what we have done, we have introduced this salt bridge. What it will do? First of all, what does it contains? So basically it is containing sodium nitrate here. The sodium plus and nitrate minus. So how does it functions? So we have prepared a agar-agar solution. Agar-agar solution, you can think it of a paste which is fluid enough to conduct the flow of our cation through it or anion through it. Now we have covered this tube on both sides with the help of cotton plug. This is our cotton plug, right? Now we have introduced Mg2 plus due to oxidation. So when there is a positive charge, it will attract the NO3 minus on this side. What it will attract? This will attract the NO3 minus of the salt bridge due to electrostatic force of attraction. Now this NO3 minus will slowly move to the agar-agar solution and will be introduced to the solution and will make NO3 minus, Mg2 plus and NO3 whole twice. Did you understand? Did you get my point? So basically I mean here is that as this Mg2 plus concentration is raised, so to neutralize it, what we have done, we have introduced a kind of same salt. Now NO3 minus will quickly move from here to here and will form, or you can say neutralize this solution. Similarly, we have this NO3 minus on this side. Now what we have done, so we have pulled this NO3 minus for electrostatic attraction. Similarly, we have a positive charge here, so it will pull the, we have a negative charge here. So what it will do, it will move toward this cotton plug and go towards Na plus, which has been left out by the NO3 minus. So since this NO3 minus are left and moved towards the solution, we have left with Na plus in the agar-agar solution. To neutralize this, now NO3 minus will move from here to here and will neutralize it wholly. So in this way, what we are doing is we are neutralizing it. So this is the function of salt bridge. So what is this? This is the function of salt bridge. Its function is to neutralize the excess negative charge and the excess positive charge on both sides by facilitating the adequate, or you can say adequate amount of positive and negative ions. So in this way it is neutralizing it, and also it is completing the circuit in a way, in a fashion, right? So this is our functioning of salt bridge. Next is our EMF. So we have seen all those things, what is electrode potential. So I have told you earlier that since we have a potential on the right side and potential on the left side, so between the two electrodes we have developed a potential difference. First potential difference was between the electrode and electrolyte interface. Now second electrode potential has developed between the two electrodes, right? And this potential difference between the two electrons of galvanic cell is called the cell potential, and it is measured in volts. It is measured in volts. So this is important. So what we have told, that due to the movement of electrons, we have seen a current. Okay, why was this electron moving? Due to development of potential difference between the two electrodes. And this potential difference between the two electrodes is called our EMF of the cell, and it is measured in volts. So this is basically the difference between electrode potential, what is the reduction potential, and of the cathode and anode. So this we will see earlier why is this reduction potential and all. It is also called, so this EMF full form is electromotive force, where no current is drawn through the cell. Okay. So what does this mean? What does this mean? So it is that EMF. So we have this electrode potential on both sides. Now as the circuit goes, this EMF get reduced and the cell get used up. But at just we have started and dipped the solution and we have connected the wire, at that time whatever be the electrode potential difference, that would be the EMF of the cell. So you should be aware about this, what I'm saying. So what I'm saying here is that what is electrode potential or the EMF? We can say that is the electrode potential always between the cell. That is why only the electron is flowing. But if we talk about specifically about EMF, we say that it is that electrode potential when we have just, you can say we have just connected the circuit and switched it on, and that instance or that small time, delta time, which we have switched this on, at that time, whatever with the electrode potential difference, that will be considered our EMF or electromagnetic force of that cell. Okay, is it clear? Yes. Now, how do we calculate this EMF? The most important and the most confusion that arises in the student is that how do we calculate this EMF? So it's very easy. For this, you need to know only one thing. Sorry, appropriately two things, right? So what are these two things? The first thing is that the reduction potential, if the reduction potential of a species is X, then the oxidation potential will be minus X. So basically the magnitude will remain same. So if it is positive for reduction, then it will be negative for oxidation. Similarly, if it is negative for reduction, it will be positive for oxidation. And the vice versa is also true. So if the oxidation potential is positive X, then the reduction potential will be negative X. And if the oxidation potential is negative X, the reduction potential will be positive X. Is it clear? Yes. Now, how we'll decide that in a given cell, which one will get oxidized and which one will get reduced? So very simple thing for it. So if one has a greater reduction potential or a greater oxidation potential, so what we will compare? So we will take both of these reduction potential or both of this oxidation potential, and if we see that one of its reduction potential is more, or of both of the reduction potential, one is having a greater reduction potential, then that substance will get reduced. On the opposite side, if we take the oxidation potential of both and we see that one has a greater oxidation potential, then its oxidation will take place. Now, how will decide that which one is having a greater reduction potential or an oxidation potential? For that, we are given a table in NCERT, and in the exams also you will get this value. Now, if you want to compare, you have to compare the exact value of that. So suppose it is written that -3 is reduction potential of one and -2 is the oxidation reduction potential of the another. So you will be asked which one will get reduced. So out of -2 and -3, we know that -2 is greater. So the reduction will take place of that species which is having a reduction potential of -2. Means we are taking the exact value along with the sign. Then only we will compare which one is greater and which one is smaller. Now suppose one is getting oxidized, so we will take its oxidation potential, and suppose the other one is getting reduced, so we will take the reduction potential. And what we will do, we will add both of these, and the summation, the answer which we will get will be the EMF of that cell or the potential of that cell. So this is the thing, the EMF of a cell will be the summation of reduction potential of the reduced species and the oxidation potential of the oxidized species. So if I want to put the formula in one nutshell, it will be like this. So reduction potential of the species getting reduced and the oxidation potential of species getting oxidized. We will add both of this and we will get our EMF or E, which is having a unit of volt. Now next we will see how can we calculate it. So we have seen the calculation, we will see how can we represent the cell. So this is our overall cell representation. So it is very useful. Okay. So children do get confused. They're given a cell potential or cell representation, and they ask which is getting oxidized, which is getting reduced. So you can get the answer of each of your question in one equation. That is this. So to understand this cell representation, first of all, so what you have to do, you have to just move from left to right in this cell representation, and that are the reaction that will take place. So the first one is saying that we are going from Cu to Cu2 plus. So if we move from left to right, we can see that we are going from Cu to Cu2 plus. Again, we are seeing here that this Ag plus is going to Ag. Ag plus is going to Ag. Means the Cu is going to Cu2 plus. It means that it is losing 2 electrons. So here is our equation. the Cu is going to Cu2 plus, means it is losing 2 electrons. Second thing, now Ag plus is going to Ag. So it is gaining an electron. It is gaining an electron and going to Ag. Now you will ask why we have multiplied this 2 on both sides. Why is it so? We can add both of this reaction independently also. So if you see here, if you add both of these equations without multiplying by 2, you will get 1 electron extra, and that is not acceptable. So after reaction, we do not have any case that we are left with 1 electron. So it cannot be used in the cell representation also. Okay. So what do? We multiply with this to this. So if you understand the physical significance of this, so 1 Ag plus will give 1 electron, and it will not be enough for Cu to go to Cu2 plus. Sorry, opposite thing. So this Cu is going to Cu2 plus. This is releasing 2 electrons, meaning that if we have to add both of these, their equivalence should be same. So if these 2 electrons are not consumed up by this Ag plus, then it can lead to a electrical neutral imbalance. So what we have taken, taken 2 moles of Ag, so that both of the electron can be consumed. Now this 2 Ag plus will take both of this electron and move to 2 Ag solid. Now it is reduction, it will take place on cathode side, and it is oxidation, it will take place on anode side. If you want to represent it using a cell representation, you can do it so. So here is our cell representation. Very easy to understand. So the substance which is going to oxidation, it is always placed on the left side. Cu is going to Cu2 plus, losing 2 electron means oxidation. It should be on the left side, and it is by convention also. So if you ever see a, say, galvanic cell, you will see that on the left hand side we have our anode, which is negatively charged, and on the right hand side we have our cathode, which is positively charged, and this is always the case. So this is always the case, and electron will flow from here to here. Electron will flow from here to here, and this is a cell convention you have to take always. So on left hand side we have our oxidized species. So this is our oxidized species. And on the right hand side, we have our reduced species. Means the one which is getting reduced. It is called reduced species. So this is the formula that we have. So it is not that much useful. You can use my previous formula that is more accurate and more generalized, and it is easier to calculate. Okay. So you can use this formula also. In this, basically what we do, we take the reduction potential of the one that is present on right, and the reduction potential of one that is present on left, and we just subtract it. So it is basically the same formula we have used, only in different manner. So we have kept the reduction potential of the right as it is, because on the right we know the oxidation takes place. So we have taken the reduction potential only. But on the left, on the right reduction takes place, but on the left oxidation is taking place. But we have taken the reduction potential. So first we will do what we'll do. We'll completely change the sign and get our oxidation potential, and then subtract it from the reduction potential to get our final electrode potential or EMF of the cell. So this is our complete reaction. Okay. Now let us go to more technicalities here. So if you see here, we are seeing a slashes here. Okay, so we have slashes, we have slashes, we have slashes. So what does this slashes represent? So there can be 2 slashes in sometimes we can have 2 slashes also. So I will make you understand what this 1 slash or this 2 slash represent. So if you talk about single slash, it is representing that we are having 2 phases. So I have introduced you earlier also that we are dipping this electrode in a solution. So we have 2 phases. The first phase of the metal block is solid, and the second phase of the solution is aqueous. So if I want to show a distinction between these 2 phases, what we have introduced? We have introduced a bar which is in between both this solution and solid phase, which is representing the cell or the phase separation. Similarly, it is on the right side also. Sometimes it is in the middle also, but most of the time we have a double slash, and this double slash means your salt bridge. So what does it mean? It means our salt bridge. So if we introduce a salt bridge, we have to maintain a double, you have to say maintain a double slash so that both of the compartment can be represented separately and more accurately. Okay, so this is our thing. So in this way, we have to represent our cell. So if you want, you can practice some example of calculation of cell potential. It will be more beneficial for you because it comes in handy with practice only. Without practice, it is difficult to control the physical chemistry. And I'm saying it one thing that NCERT is much more enough for your physical chemistry overall. Whatever I have till date studied, it is much more having greater potential than we have underrated. So that is another topic. For now, this is our cell representation. So if I get a revise for all of you, so what we started from galvanic cell. So what does galvanic cell does? It converts our Gibbs free energy of the spontaneous redox reaction to electrical energy. Now we have an interface between the electrode and electrolyte, and both have the tendency to go from one phase to another, from solid to liquid, from liquid to gas. So from solid to liquid and liquid to solid. From solid to liquid, 2 electrons are released. From liquid to solid, 2 electrons are accumulated. Now what we have done, we have taken that 2 compartments are connected and created a potential difference between both of the electrode. Now the ones which has a greater tendency to lose electrons and go into the solution will be forming electrons, and the one which has a smaller tendency to lose electron and the greater tendency to accept electron will gain the electron that were released, and overall we will have a neutralized charge, and this is called, overall we have a electrode or a EMF of the cell. So what is this EMF? It is the difference between the electrode potential of both sides just before the reaction has started or the switch is on. Okay, so in this way a galvanic cell works. Next we have seen what is salt bridge. What is salt bridge? It is basically something that is doing several key roles. First off, it is completing your circuit. Second, it is completing the circuit first, and the second is that it is maintaining electrical neutrality. Third, since we have a salt bridge, we do not have to mix both these solutions, so we are preventing mixture of both the solutions. Then we have seen this EMF calculation. So calculation of EMF basically means we are taking the oxidation potential of that species which are getting oxidized, and we are taking the reduction potential of that species which is getting reduced, and we add both of this. Now if you want to know the oxidation potential and you do have the reduction potential, you will just take the opposite sign with it, and then you will get your reduction potential. Now suppose you have your reduction potential, you want the oxidation potential, you will just take the opposite sign and just pick it and just over. Okay, so this is the thing. Next is the cell representation. So the most important thing to remember here is that we have to put double slash to represent the salt bridge. So this salt bridge is basically representing our double slash is basically representing our salt bridge, and the single slashes that are present on both sides are representing the phase separation. So it is a kind of interface between the electrode and the electrolyte, and this is our cell potential. Now if I want to make one more thing clear here, so in the previous class you must have seen that I put a negative charge on the left hand side, but anode is not negatively charged, it is positively charged. This negative sign represents the electrode potential. It has a negative potential. Okay, this is representing a negative potential of the anode. What do you mean by negative potential? It is basically the potential of that electrode to give electron. Okay, so it is kind of negative potential. It is not that this anode is negatively charged. Okay, so this should be kept in mind that it is not negatively charged. It has a negative potential. And why it is negative potential? Because it is losing electron. Similarly, on the right hand side we have our cathode, which is, of course, this electrode is, so this cathode is negatively charged, but it has a positive potential. Why? Because it has a tendency to gain electron. But it has a tendency to gain electron. So this cathode is have a negative potential. Sorry, negative potential, not positive potential. This cathode has a negative potential, positive potential. Sorry for the confusion. Anode has a negative potential and cathode has a positive potential, whereas anode has positive charge and cathode has negative charge. Is it clear? So this positive sign is for the potential representation and not the charge representation. Okay, so this was for today's class. So we have seen the EMF of a cell. So in the next class, what we will be dealing. So we'll be dealing mainly with our discuss this cell representation. We will see the Nernst equation and all, and our relation of the EMF of the cell with Gibbs free energy. So those things we will see in the upcoming lectures. So for now, this is our whole thing. Thank you for your time.